Hello everyone, in this video we'll be talking about the damped oscillation. Before we dive deeper into the topic, let me ask you four brilliant questions. Question number 1. Here you can see the Taipei 101, the tallest skyscraper of the Taiwan. It has 101 floors above the ground. In between the 88th floor and the 92nd floor, there lies this steel sphere. The diameter of this steel sphere is 18 foot and it is made up of 41 steel plates. Its mass is 660 metric ton, means 6,60,000 kilograms, and it swings as a pendulum under the computer control. What's the purpose of this device and how does it work? That's the question. If you have any idea about it, let me know in the comment box. The second important question, you see the two shock absorber like structures here in this building. What's their purpose? Okay, let me know about this also in the comment box. And here is the third question. How does a spider knows the location of an insect in the web? And there comes the last fourth question. You see there is an uneven road and the biker is holding the handle firmly. If the biker leaves the handle, keeps the hand in the air, what will happen to the geography of the biker's face? And what advantage the hands give you over the handle? Whatever idea you are getting about it, let me know in the comment box. Most of the everyday oscillations are damped. You can see so many examples. Suppose you leave the keys in the lock and then they swing. Their oscillation is actually damped. After some time, they finally stop. You take the example of a swing. The swing will oscillate and after some time, it will settle down at the stable equilibrium position. You can take the example of the shock absorber of a vehicle. So, most of the everyday oscillations are the damped. Here is the first example. You can see a block connected with a spring. The mass of the block is m and the spring constant is k. This block oscillates in the presence of the air. As we know, air imparts the resistance to the motion. So, gradually the speed of the block will keep on decreasing, as well as its amplitude will also decrease and its time period will keep on increasing. Although that change will be very small, we cannot usually observe that. That I'll prove through a question also in this video. Okay, this kind of oscillation is known as the underdamped oscillation. In such oscillations, the system does the to and fro motion about the stable equilibrium position. Its amplitude keep on reducing and finally it comes to stop. Okay, can you suggest me some other examples of the underdamped oscillation? Correct, the swing is an example of the underdamped oscillation. The keys, the oscillating keys in a lock, they are also the example of the underdamped oscillation. And I request you to observe few more daily life phenomenon where you can find out the underdamped oscillation and let me know in the comment box. Now, taking up the second scenario, the same block having mass m, the same spring having constant k, but this time the block oscillates inside the water. The water will impart greater resistance as compared to the air. So, the amplitude gradually decreases and its time period increases as well as the frequency of oscillation decreases. Initially, the oscillator has more mechanical energy and since its speed is greater, its mechanical energy is greater, it will dissipate more amount of energy because you already know faster an object moves through the air resistance, it will lose more and more energy. So initially the difference between two successive peaks is greater. Later on it has lost most of its energy to the friction or to the air resistance. Then the difference between two successive peaks will be smaller because now it has less amount to lose the energy. Got it? Now we take up the third example. The same spring having constant K and the block has the mass M. The mass M has been pulled down little bit and released. Let me know, will it complete one cycle? What do you think? Honey is thick. Honey can impart a great resistance to the motion of the block. Okay, the correct answer is this mass will not be able to complete one cycle. From whatever position you will release that mass, it will slowly move towards the stable equilibrium position and it will settle down there. It will never overshoot or it will never go across the stable equilibrium position. This kind of motion is known as the over-damped motion. Okay, in over-damped motion, the important thing, it will not perform the oscillation and it will go to the stable equilibrium position very slowly. Okay, now we are taking up the fourth example. Suppose there is a spring having constant K and a mass M is attached to this spring as shown. The block is displaced and released. What do you think? Will it be able to complete a cycle? The answer is no. In the oil, the block will not complete one cycle. From whatever position you release the block, it will go to the stable equilibrium position and will stay there. It will never ever overshoot the stable equilibrium position. This kind of motion is counted under the critical damping. In the critical damping, the object returns back to the stable equilibrium position in minimum possible amount of time and it does not oscillate. So if someone asks you what is the basic difference between the critical damped motion and the over damped motion, the answer is simple. In the critical damped motion, the system reaches to the stable equilibrium position in the minimum amount of time, while as in over damped motion, it will take a great amount of time to reach the stable equilibrium position. Is it clear? And what is the similarity in between the critical damped motion and the over damped motion? Can you tell? Correct. In both the cases, the system will not oscillate. System will never complete a cycle. Okay. Now I am going to derive the mathematical expressions or the relations for the damped oscillation. So let's start the calculation on the board. Here at this position, initially the net force is 0 because the normal force and the gravitational force, they are balancing out each other, and since the spring is in its natural length, so the spring force is also 0. Is it okay? In order to start the oscillations, we will displace this block, let's say up to here, and at t is equal to 0, the block is released. This distance we are naming as the A. Now the block will perform damped oscillation. Since the air resistance is present, it will never ever return back to this same position here. Its amplitude will gradually decrease, as well as its mechanical energy will also decrease. Okay. Now suppose at some time t, we draw again the diagram. This is x equal to 0 and at time t it is x away from this initial position. Okay, you can treat this as the origin. For calculation purpose, you will be taking up this direction as positive and this as negative because it is the one-dimensional motion. Okay. Now the forces acting on this block, since the spring is elongated here, so the spring force will be in this direction. Do you agree? And its velocity is, let's say, in this direction. Then the damping force due to the air should be in the opposite direction. Is it okay? That is by the practical experience. Suppose you are running in the forward direction, where do you feel the air resistance? In which direction do you feel the air resistance? You'll feel the forces of the air resistance in the backward direction. And another observation, the faster you move, you will experience more and more force in the opposite direction due to the air resistance. So here, for this damping force, we can write few important things. For small speeds, the damping force has been observed directly proportional to the speed. And if we remove the proportionality, here comes a constant. Fd can be written as Bv. This B is called the damping constant or damping coefficient. The damping constant or the damping coefficient depends on various parameters such as the viscosity of the surrounding medium, the shape or the size of the block. Okay. Now, in order to do the mathematical analysis, we will be using the Newton's second law along the horizontal direction. So first of all, I am writing the net force on this block in the horizontal direction. This F net should be written equal to F restoring plus F damping. Do you agree? Okay. F net can be written as Ma. The restoring force is due to the spring. The block has the velocities in this direction, but the spring force is trying to pull it back toward the x equal to 0. So the restoring force should be written as Kx, but with a negative sign, because the spring force is in this direction and this has been chosen as negative. The damping force will be written as minus Bv. This V can be written as d by dt of x, as well as the acceleration can be written as d2x by dt square. Do you remember these things? So doing the replacement here, m d2x by dt square is equal to minus kx minus v d by dt of x. Shifting all the terms here in the RHS to the LHS. So m d2x by dt square plus b d by dt of x plus kx is equal to 0. This is a differential equation. And when we simplify this differential equation, we'll get the solution as x is equal to a e to power minus bt by 2m cos omega dash t plus phi. Okay. This part will be known as the amplitude, and this is known as the angular frequency of the damped oscillation. Now, if we look at this function, the cosine function is a periodic function, but the amplitude of this will keep on decreasing. For small damping, we can take the period to be nearly constant, and we can write the value of omega dash also. The omega dash will be equal to root of k by m minus b by 2m whole square. Using the value of omega dash, we can talk about the critically damped, under damped as well as the over damped motion. So I request you to note it down up to here, and then we'll take it further. Taking up these values further, suppose this k by m minus b by 2m whole square is equal to 0. Then what value we will get? We will get b is equal to 2 root m k, and this is known as the critical damping. If this condition is satisfied, the system will not perform oscillation. Once it is released, it will settle to this position x is equal to 0 in the minimum possible time. It will never ever overshoot. Okay. Example of this critical damping. The shock absorbers of the vehicles, they are also critically damped. If the shock absorber was to be under damped, you can feel it will be very bad for the vehicles, because once the shock absorber got some compression, then it will take time to settle down. Its oscillation amplitude will keep on decreasing, and that is not good for the vehicle. Once it's hitting a pothole, and then for a longer period of time the shock absorbers are oscillating, that's not good. And the shock absorber must not be over damped. If you remember, for over damped situation, once released, the particle takes a great amount of time to reach back to its initial position x is equal to 0. So suppose, let's say a shock absorber is getting compressed, and then it is taking a lot of time to reach back to its initial situation, to reach back to its initial position. And in between that time period, if there is another pothole, then what will happen? The shock absorber is still compressed, so it cannot fully absorb the jerk. So keep in mind, the shock absorbers are the critically damped. I'll give you another beautiful example. Look at this robo dog. Pay attention to this video. The robo dog is performing a back flip. Now what do you think about the legs of this dog? They should be over damped, they should be critically damped, or they should be under damped? The legs of this robo dog should be critically damped. Once they are released from a certain position, then they should quickly reach back to the initial position for optimum operation of this robo dog. I hope you got it. I'll give you another example. Look at these robotic hands. Their operation should be critically damped, under damped, or over damped. Simple logic. From one given position, they should reach back to their initial position in minimum possible amount of time for the efficient operations. It means these robotic hands are critically damped. There are thousands of the examples of the critically damped motion. If you find some, let me know in the comment box. Now going further for the next condition, suppose the B is greater than 2 root mk. This condition is called over damped. If B is greater than root 2 mk, you put the data here, you will find that omega dash will come out to be some imaginary number. It means there will be no oscillations. Okay, even in the critical damping, there are no oscillations. Taking up a great example on the over damped motion, the heavy doors in the public places are actually over damped. Once the door is released from a certain position, then it should just stop at its closing position. It should not go beyond that. So the doors which close automatically using the hydraulic mechanisms, all those doors are over damped. Okay, once released, they'll slowly move towards their closing position. Done? You may note it down, then we'll go further. Do you remember the difference between critical damping and the over damping? In critical damping, the system reaches back to the initial position in minimum time, and in over damping, it takes a great amount of time to reach back to the initial position, the equilibrium position. Okay. Now another possibility, what if B is less than 2 root mk? This case is known as the under damped, and in this case system performs the oscillations, but the amplitude will keep on decreasing. The mechanical energy of the system is lost to the friction or the air resistance or to the dissipating forces. Fine. We have taken the numerous examples. So up to here you can note it down, and then we'll go for the energy of the damped oscillation. Due to the decrease in the amplitude of the oscillator, the total mechanical energy of the oscillator also decreases, and you can see the expression of the total mechanical energy here. Looking at this expression, few people might think that the total mechanical energy will be decreasing smoothly and exponentially, but that is not the case. It is pretty important, so pay extreme attention. See, if we talk about the damping power, then the damping power will be written as damping force dot V. So the damping power will come out to be minus BV square. It indicates that wherever the velocity is zero, the damping power is zero, means no energy is lost. So when the oscillator is at the extreme positions, there is no energy loss because the velocity is zero, and if velocity is zero, then the air resistance will not cause any energy loss. I hope you understand this thing. So the energy will decline stepwise. You can observe this graph very carefully. Check the total mechanical energy. It is not decreasing smoothly. Okay. Here we can see a simple question on the screen. So I request you to pause here and give it a try yourself, and then I'll be simplifying it. I hope you all got the correct answers, which is the set 1, then set 2, and then set 3. Why? Let's see the solution here. First of all, let us write the expression of the total mechanical energy. More you write, better you will understand. So let's write half Ka square e to power minus Bt by m. That is the expression. And the initial mechanical energy can easily be obtained by putting T is equal to 0 in this expression. So half Ka square e to power minus B into 0 by m. E to power 0, everyone knows, is equal to 1. So this is the initial mechanical energy. According to the question, at some time t, the total mechanical energy, which is half Ka square e to power minus Bt by m, is equal to 1/4 of the initial mechanical energy. Do you agree with this? Pay attention to the language of the question. At some time t, the total mechanical energy is 1/4 of the initial total mechanical energy. Okay. Now we are going to simplify this. One thing is interesting here. Half K square is getting cancelled out. So we are left with e to power minus Bt by m is equal to 1 by 4. Now in this expression, if we do the calculation and we simplify the things, then time will depend upon m by b only. So in this question, the k has no role. K is appearing nowhere in this expression. It means the time depends only on these two parameters. We need to check the ratio of m by b. Now the ratio m by b is greatest in the set 1 and is least in the set 3. So here is our answer. Here is an interesting insight. If someone asks us at which moment of time the total mechanical energy will become 1 by 6th of the initial total mechanical energy, then that time will be independent of k. Even for any such question, suppose someone asks us the total mechanical energy becomes 1 by 10th of the initial total mechanical energy, this will happen at which moment of time? Again your answer will be independent of k. Getting it? You may note it down and then we'll go further. Here is the next question. So again, I request you to pause here and try to post your answer in comment box. Then we'll be simplifying it. I hope you got the correct answer, which is 75%. The computation is pretty simple. We know one thing, that the total mechanical energy is proportional to the amplitude square. Do you agree with this? Now, if we look carefully at the graph, then as compared to the first peak, the second peak lies almost at the half level. What do I mean to say? If we pay attention to the graph, if this is at the level 3, then this peak is lying somewhat at level 1.5. I hope you get it. If amplitude becomes half, it means the energy will become 1 by 4 of the initial, because here is the amplitude square. So if amplitude becomes 1 by 2, then energy will become 1 by 4th of the initial energy. Getting it? So it indicates that the final mechanical energy is equal to 1 by 4 of the initial mechanical energy. Do you agree? Okay, as the amplitude became half. Now, if you are left with 1/4 of the initial mechanical energy, it means how much energy has been lost. That can easily be written here. Loss in the mechanical energy is equal to 3 by 4 of the initial mechanical energy. And 3 by 4 means how much? 0.75. So if you want to write in the percentage, it indicates that 75% of the initial mechanical energy has been lost. Okay, you may note it down, then we'll go further for the next one. This one is also a simple question, so give it a try. I hope you got the correct answer. Due to the introduction of the damping force, the angular frequency of the oscillation will decrease by 20%. Let's prove it. The solution is pretty simple. Without damping, the omega is equal to root k by m. We know the values. K is 50, m is 2. So omega comes out to be 5 radian per second. Okay. And with damping, we'll get the omega dash, which will be equal to root of k by m minus b by 2m whole square. Okay. Let us simplify it. K is 50, m is 2, b is given as 12 divided by 2 into 2, and here is the whole square. Simplifying this, the omega comes out to be 4 radian per second. So how much is this decrement? From 5 radian per second, the value becomes 4 radian per second. Few smart people can directly tell the decrement is 20%. Although we can do the calculation. Suppose you want to calculate the percentage change. It means what? Final value minus the initial value divided by the initial value into 100%. Just a simple formula. Let us put up the data. Omega dash is 4, omega is 5 divided by 5 into 100%. This computation comes out to be minus 20%. Minus 20% means what? The angular frequency has been reduced, has been decreased. Okay, note it down, then we'll go further. Here is another simple question, so I'll wait for your answers. I hope you all got the correct answer, which is 1 by 9 of the initial amplitude. Let's see the solution here. We already know the function of amplitude. We require the initial amplitude. For initial amplitude, we should put here the t is equal to 0. E to power 0 becomes 1. So finally the initial amplitude is a. And if you remember the starting of our derivation, the initial amplitude was a. Okay. Now, suppose the time period of one oscillation is equal to capital T, then how much is the time period for 100 oscillations? 100 T. How much is the time period for 200 oscillations? 200 T. Time period for 1000 oscillations? 1000 into T. Getting it? According to the question, the amplitude becomes one third of the initial amplitude. One third of the initial amplitude. After what time? After time 100 T. After 100 oscillations. So we should write this as A e to power minus B into 100 T divided by 2m. I hope you understand it. I am explaining it again. According to the question, after 100 oscillations, means 100 into T, the amplitude becomes one third of the initial amplitude. Is it okay? Call it equation number 1. Now, again, according to the question, after some time, the amplitude is, let's say, A dash, and A e to power minus B into 200 T divided by 2m. When it completes 200 oscillations, the time taken is 200 T, and the amplitude at that moment of time is, let's say, A dash. This is equation number 2. Is it okay? Now we can divide these two equations. The A dash will come out to be A by 9. I hope you all got this answer, and I am explaining the details of the calculation here. See this expression, I am taking it again here, the equation number 1. A and A is getting cancelled out, so you can write 1 by 3 is equal to E minus B into 100 T divided by 2m. Do you agree? Do the square both sides. Then we are left with 1 by 9 is equal to E to power minus B 100 T divided by 2m whole square. And when you simplify it, it will look like E to power minus B, and this will become 200 T divided by 2m. Is it okay? Now, if we check this expression, the second equation, pay attention here, this expression E to power minus B into 200 T divided by 2m. At the place of this data, we can bring here what? 1 by 9. So the answer became A by 9. I hope you understand it. You may note it down and then we'll go further. Here we have the another beautiful question. So if you wish, you may give it a try and then I'll be simplifying it. I hope you are done with your calculations. So let's proceed for the solution. This position is the stable equilibrium position. Can you guess why? Because here the net force is 0. If you check at t is equal to 0, let's say, the normal force and the gravitational force are balancing here. The spring is in its natural length, so the spring force is also 0. So this is the initial stable equilibrium position because here the net force is 0. Now at t is equal to 0, a sharp kick is given in the horizontal direction. Due to that kick, the block will acquire some speed, we call it v, and then block will go somewhere. This will be the extreme position of the block, and here again it will attain momentarily rest. Getting it? Due to this velocity, it will go further. But the spring force was acting in the backward direction, the air resistance or the resistive force was also acting in the backward direction, so it will slow down and it will come to momentarily rest here. This distance we are naming as A. Is it okay? Now here the impulse given was known to us, which was equal to J naught. So J naught can be written as the final linear momentum minus initial linear momentum. I am writing the impulse momentum theorem for this mass m. The final linear momentum can be written as m times v, and the initial linear momentum is 0 because initially the block was at rest. So J naught is equal to this. Is it okay? Now, if we remember about the SHM, then at the stable equilibrium position, the V and this A are related. Do you remember something? Correct. We should write here V is equal to A omega dash because this motion is damped. So I am using the omega dash. Is it okay? Submitting the value of V here, J naught is equal to m A omega dash. This will give us the value of A. We'll be using that value of A in the further calculation. Now, the system will start its motion from the position x is equal to 0 and it's going towards the right. For such an oscillation, the initial phase phi is equal to 0. So, the equation will be written as x is equal to a e to power minus bt by 2m sine omega dash t plus phi. Do you get this? And this is for t greater than equal to 0. The a can be brought from here. It is J naught by m omega dash e to power minus bt by 2m sine omega dash t plus phi. Okay, this phi will be actually 0 because it's starting from the initial stable equilibrium position and going towards right. So in next step I'll put that phi as 0. Submitting the values, J naught by m. What is the value of omega dash? We remember omega dash will be equal to root of k by m minus b by 2m whole square. Do you agree? E to power minus bt by 2m sine of omega dash t, and value of omega dash we already know. Okay, this is the value of omega dash. Here is the x as a function of time, and this function is valid for t greater than equal to 0. Okay. Now suppose if you want to write the function of x for t less than equal to 0, then t less than equal to 0, the block was at rest. So its x coordinate will always be 0. Okay. This is our omega dash, angular frequency for the damped oscillation. Simple but nice question. You may note it down. Then we'll be taking up the last question of this video. It's an important question, so I'll be simplifying all the parts once you pay attention to the language of the question. Okay, let's write the solution for the first part of the question. We are working with the damped oscillation, and we already remember the formulas for the damped oscillation. The omega dash comes out to be root k by m minus b by 2m whole square. Do you agree with that? We have all the values and we are using the SI system. So k is given as 90, m is given as 0.2 kg. The gram has been converted into kg. Minus b is given as 0.04 divided by 2 into 0.2, and then here is the whole square. Okay, you can compute it and you'll get the value of omega dash. Is it okay? Now, after getting the omega dash, we can find the t dash. T dash will be equal to 2 pi by omega dash. and this is the answer for the t dash. If the motion was to be undamped, then what will happen? Let us check that once. For undamped oscillation, we know one thing, that the damping constant B will be equal to 0. If we put B is equal to 0, then omega will come out to be root of K by M, and we know all these values. K is given as 90, M is given as 0.2. Okay. After getting this omega, you can find the time period, and that will come out to be 2 pi by omega. Okay. If we compare t dash and t, what do you notice? There is one interesting insight, that after the decimal up to 5 digits, the answer is equal. So, if your measuring instrument cannot measure the time period after the decimal up to 5 digits, then you won't even notice that these two are the different things. I hope you get my point. So this motion can be treated as approximately periodic. Done. And what is happening in reality, if you check it, t dash is greater than t. The omega dash is less than omega, as well as the f dash is less than f. Getting my point? If you check another insight, that value of K by M is much smaller as compared to B by 2M. Omega dash is approximately equal to omega, T dash is approximately equal to T, and F dash is approximately equal to F. Do you agree with these answers? So it's an interesting question. I request you to note it down. Then we'll proceed further. Now, simplifying the second part, and it's pretty important, so pay attention. We know the amplitude of the damped oscillation can be written as A e to power minus bt by 2m. The initial amplitude can be written equal to A e to power minus b into 0 by 2m. Put t is equal to 0, then we'll be getting the initial amplitude. E to power 0 is always 1, so the initial amplitude will come out to be A. According to the question, after some time, the amplitude becomes half of the initial amplitude. So I am writing that mathematically. Half of the initial amplitude, A e to power minus bt by 2m. See it again. The amplitude becomes half of the initial amplitude at some specific moment of time, and this I am writing intentionally t half. Okay, we call it actually half-life. Similar things you will see in the chapter radioactivity. Okay, now proceeding further, A is getting cancelled out, taking logarithm both side. So here we are left with ln1 minus ln2, and here log and anti-log will get cancelled out. So minus b half-life divided by 2m. This ln1 is 0. This negative sign and negative sign will get cancelled out. So we'll get the value of half-life. It will be equal to 2m by b ln 2. Super important expression. You might learn it if you wish. Okay. In this much time, the amplitude of the oscillation will become half of its initial value. Now, in order to obtain the number of cycles, we divide this half-life by the time period and we get the number of the cycles. The number of cycles are coming out to be somewhat greater than 23. It means after 23 full oscillations, okay, more than 23 oscillations, the amplitude will become half of the initial amplitude. It's a simple but interesting question. You may note it down, then we'll go further for the last part of this question. First of all, we should write the formula of the total mechanical energy. Do you remember? The total mechanical energy can be written as 1 by 2 Ka square e to power minus Bt by m. Is it okay? We need the initial total mechanical energy. So for that, in this expression, we can put T is equal to 0. So it will look like 1 by 2 Ka square e to power minus B into 0 divided by 2m. E to power 0, everyone knows, is equal to 1. So the initial total mechanical energy is half Ka square. Okay. According to question, at some moment of time, the energy, which is half Ka square e to power minus Bt by m, becomes half of the initial total mechanical energy. I'll explain it once again. Just pay attention. Question says at some moment of time, the total mechanical energy of this system becomes half of the initial total mechanical energy. Is it okay? Now it's a simple computation. This 1 by 2 Ka square and 1 by 2 Ka square is getting cancelled out, and then we can take logarithm both sides. So it will be ln1 minus ln2 is equal to minus Bt by m. ln1 is 0. This minus and minus will get cancelled out. So T comes out to be m by b ln 2. You'll notice one interesting thing. This time is exactly half of the half-life. Can you tell why? Post your answer in comment box. And if you need to find that after how many cycles the total mechanical energy will become half of the initial total mechanical energy, then you can compute it like this. You may note it down. Now, I'll be answering the 4 opening questions of this video. The first one was regarding the Type A 101. Actually, this device, I hope till now you understood, is a damped oscillator. In the case of the vibration due to the high winds or due to the earthquakes, this pendulum oscillates in the opposite direction of the resonant frequency and keeps the building structure intact. Okay. The second question was about the large dampers. They also absorb the energy of the earthquakes and keep the building structure intact. Okay. Now let's check the answer of the third question. How does a spider locates the insect inside the web? Actually, when an insect comes to the web, due to the entry of that insect, the web will start oscillating. It will be a damped oscillation. Now suppose the insect is far away in the web, then those oscillations while reaching to the spider might damp out. Then spider will not know anything about the location of the insect. But if the insect is bit closer and the damped oscillations are sensed by the spider, then spider can locate the insect. And the last fourth question, what is the advantage of putting the hands firmly over the handle of a bike? Actually, due to the unevenness of the road, there are oscillations, and these oscillations are damped in the wrist and then here and then here. So if a biker is holding the handle firmly, those oscillations, their energy is getting damped here, so you can gain better control on the bike. Now suppose the biker is performing a stunt, he keeps the hands away, and then due to the unevenness of the road, there is a jerk, the bike might lose its balance. It will change the geography of the face of the biker. I hope you enjoyed the video. Now you'll be observing the answers of the checkpoint questions. Stay awesome. See you again.